It's really a great pleasure to be here, and as Tony said, there's the title of my talk, various places to thank, and I really want to make sure to thank the Institute of Advanced Studies, because that's what has allowed me to come here to UWA, and it's really a great pleasure to be here. So you can see what I'm going to do today is talk about Earth and Venus. Also want to thank just all kinds of students and colleagues that I've worked with, and two notably from UWA through the years here. So the big question that I want to try to address is, how did Earth's cratons form? And I'm going to put right up front where I'm going with this, and that is that I am going to use Venus as a potential analog to help us to understand how the cratons might have formed on Earth. And the reasoning is that Venus is Earth's sister planet, and she's similar in size, density, composition, heat budget, solar location, and these are the first-order critical factors that affect early planet evolution. And the logic thread is that the Earth has destroyed a lot of its early record. Venus has preserved essentially many pages of that early baby book, and because they were most similar in their early days, this would be a good way to look for clues about the Earth from Venus. And very specifically, we're going to look at a kind of feature called Crustal Plateaus. So I'll tell you what those are, and I think that they are analogous in some ways to Archean cratons. So, as we all know, today, plate tectonics is how our planet cools itself. And when we go to the past, what we've been taught in geology is to use uniformitarianism. Present-day processes are what we're going to use to interpret the past. And I am going to put right out front, I don't think this is a good approach for the early Earth, or at least say, let's try another way to get at that than just uniformitarianism and start with plate tectonics and move it backward. So I'll put that right out there. What I want to do is to start with the record that we have of the Earth. And when we go to the Archean, as I'm sure most of you know, that Archean record is extremely limited. Less than 10 million square kilometers, and there they are in black. And if you know many of these places, the exposures are not all that great across those black regions. So even what we see is extremely limited. Despite that, all of the Archean that we see at the surface has some real similarities that make these distinctively Archean rocks. And people have recognized that for a long time. And specifically, they're the granite-greenstone terrains and their associated gneissic terrains. If we look back in the 1950s, mapping from you can read it there, I can't say it, craton in Rodinia, we could see just the characteristics of these granite-greenstone terrains. Within white, the domical granites, broadly meaning more felsic rocks. We now would call them TTGs and other things, but felsic rocks forming domes, and in between those domes are granite-greenstone terrains that are forming folded keels between them. This is a different type of style that we have in younger rocks. Many here might be more familiar or equally familiar with the Pilbara craton. We also have other ways of looking at them here in a false color Landsat image. But again, we see the domes there and the granite-greenstones around them. If we go to the Superior Province, here we've got the Superior Province up in Minnesota and Canada, which I am from, here in Duluth, Lake Superior. And I've put in the Pilbara there, and Rodinia and the Dewar Craton. These are all at the same scale, and we see real similarities between them. Within the Superior Province, we can simply see a larger footprint of this whole type of terrain. I want to focus on and you've got up here the granite-greenstone terrains in the greens and the grays, and then higher grade gneisses in belts that we see here. If we look at the Abitibi, in this region there, we can zoom in on that geology, and we see domes of granitic type rocks in the pinks here, and in between those we see the granite greenstone terrains, mostly in the browns and the greens on this map. What Phil Thurston and his colleagues have shown is that when we look at those metasediments and volcanic packages, they all have young upward away from the granitoid bodies. We can also see that at this scale we broadly see essentially an up warp here, down warp there, up warp. So I've drawn the axis of broad folds or warps across this terrain. That's going to come into play later on. So I've just compiled here the characteristics of granite greenstones. And you guys can read these a whole lot faster than I can go through those. So I'll just let you go ahead and do that. I want to highlight a couple of things that we've got. Komatiites are common. We've got the TTGs. We've got stratigraphic up. We have a lack of high P metamorphism. And volcanism and magmatism were coeval throughout much of it. So this is what the Archean represents from the surface as we look down. But it turns out that there's also a unique signature of Archean cratons from below, and those are summarized in this cartoon here. So on the surface, we've got the granite greenstone belts, but as we look in the root down below that's supporting this, this is called a number of different things in the literature, from subcontinental lithospheric mantle to cratonic lithospheric mantle, and about every combination that you have. I've kept cratonic lithospheric mantle here for the Archean craton. And these are different from their younger counterparts. They're Archean in age. They're very high magnesium, and because of that, they are very buoyant, extremely strong. They're dry. The diamonds that are associated with this are actually different than the diamonds that are associated with the younger lithosphere and the subcontinental mantle lithosphere, marked by primitive carbon, and associated with this high magnesium rock. So we know they come from those roots. So we look at this, what turns out to be not completely accepted. There's a lot of debate on the Archean, but broadly accepted is that when we talk about craton, what we mean is the granite greenstone and gneisses above, and these cratonolithospheric mantle below. Many would say that the cratonolithospheric mantle here is what's responsible for the preservation of the granite greenstone terrains. I like to think of it as essentially a life preserver that is, if they are attached to one another, we're going to preserve that granite greenstone terrain. If they become detached, the granite greenstone terrain will disappear. And there seems to be growing support in the literature that these two parts of a craton broadly formed at the same time and are genetically related. The process of their formation is, there's not a lot of agreement, at least broadly across the literature. And I want to highlight two recent hypotheses here that both explain or address coupled granite greenstone and that cratonolithospheric formation. It's interesting that both of these agree on certain things. They try to form non-arc basalt, which is in the granite greenstone terrain, and the cratonolithospheric mantle, and they both require or employ from the data very high temperature melting and very high fractional melting of the mantle. That's going to be really important. They end up doing that by different mechanisms, but they use this, to me, here are their data. I won't go through, but you can probably see that these points here are pretty similar. They're using exactly the same data. They don't disagree on data at all. They do use different assumptions about the temperature of the Archean mantle and things like that. But those are assumptions. They're things we don't know. But they do agree that we require very high temperature melting, high fractional melting. One of those hypotheses does it by saying that we have very high temperature melting in extremely hot mid-ocean ridges during the Archean. And the other forms these by a Archean plume. I don't want to get into a discussion of pros and cons of either of these hypotheses. They both have pros, they both have cons. But what I want to propose instead is perhaps another hypothesis. And so I want to say we've got to start somewhere. I'm going to start with the same assumption that we're having coupled formation of the granite-greenstone terrains and their roots. And I'm going to defer to the petrologists and say that in order to do this, we have required very high temperature melting in the mantle and very high fractional melting. They've looked at the data on Earth. The data on Earth that they get that from is the basaltic compositions, the komatiite compositions, and the compositions of the craton-lithospheric mantle. I say, well, is there anywhere else that we can go for some possible clues? And as you know from my beginning, where I'd like to go is to another planet, and that is to Earth's sister planet, Venus. And I went through the logical thread for why we would go there. When we look at planet evolution, just as when we look at human evolution, two kids are the most similar at birth, and two planets are the most similar at birth. And Venus and Earth are similar in the most important ways in terms of what is going to be important for how that planet evolves. So if we start them very much the same, that early evolution is going to be the same. They now are quite different from one another. Venus never developed plate tectonics, and because of that, she records a much richer record of those earlier years than Earth does. So we've got to talk about what do we know about Venus in order to use these great clues. And we actually have learned a lot over the last 20 years thanks to an incredible mission, the NASA Magellan mission to Venus. The data sets are up there: radar, altimetry, gravity, and emissivity. Emissivity is in brackets because it's a data set that we have not really cracked the code on yet. It's, the global data set is way too complicated. There are too many things that, parameters that feed into it. But all of these are global data sets, and the richness comes in looking at them together. The setting on Venus is here. It's very hot any way you measure it. It's a high pressure that's similar to about a kilometer depth of the oceans. It's extremely dry. The atmosphere is almost all carbon dioxide. It actually mists sort of a sulfuric acid. Not a great place for holidays. The atmosphere is supercritical under these conditions. That makes it interesting because there are probably things that actually at a first order boundary condition, things work differently. There's essentially no surface winds. It's the same temperature everywhere. The day is longer than the year. So Sophie Kemp just had her birthday the other day, and we went to Venus, and she would have 2 birthdays in one day, essentially, if she were on Venus. And the surface we take is to be basaltic. What all of this results in the broadest way is Venus is ultra dry. There's no water. Because there's no water, there's no erosion. That means, and there's no burial. That means what is at the surface, we see the surface effects of whatever are the dynamic processes that happen. So keep that in mind as we look at images. There are no plate tectonics, so there was no massive recycling of the lithosphere. That's also a bonus when we're trying to understand the early part. Now, it does have an incredibly detailed surface. It takes work to try to understand that geologic history, but I think that we can do that. It's just exactly the perfect playground for geologists. So here is the radar data set. Almost for the glasses, not quite with the movie, sorry. So SAR stands for synthetic aperture radar. This is an incredible data set. It's 100 meters per pixel. 98% of the planet is covered. The bright areas are radar rough. The dark areas are radar smooth, and those black stripes are the noodles. And that's the technical term they use. Those show the track of the spacecraft. You guys probably know that Tidbinbilla here in Australia, in Canberra, was really important in receiving a lot of this data. And what I want you to see at this point is, first of all, that's pretty impressive data set. We have nothing like this on Earth. Why not? Because we can't see through to the oceans. We have no resolution equivalent data set like this on Earth. But what hopefully you can also see is this is not a homogeneous, boring surface. There's actually a lot going on that planet. There's a lot of history recorded. Okay, now you can put on the red-blue glasses. And these are synthetic aperture, synthetic radar images. Some of them are synthetic stereo images. Some are true stereo. It doesn't really matter to what we're doing here. To just get you oriented, this should be a big hole in the ground. Oh, blue goes on your right eye. If you want to have fun, flip your glasses over, and this is going to be a big mound instead of a hole, but then put them on right way. So the blue is on your right eye. That should be a hole. Everyone see the hole? Yeah, okay. This is, and then we've got ejecta. This is a big impact crater. There's a scale over there. We've got ejecta out here. It's radar bright, so that means rough. And then this is melt that came in because this impactor, when it hit, probably hit a pool of magma at depth. The way the radar works is you can think of it as a flashlight. We have an energy source from the spacecraft, and it goes down like a flashlight. If it's a very smooth surface, that light is going to be reflected away. No energy will be collected by the spacecraft, and hence it will be dark. If I take that mirror, break it up, it's got pieces in all different directions. I shine my flashlight down, and that light is going to be all scattered. A fair bit of it will come back to the spacecraft. Hence, radar rough at the wavelength of the radar. The other thing is if I take that mirror and turn it toward the spacecraft, then the mirror will reflect all of it back. So if surfaces are tilted toward the radar, they will also be bright. Venus has the best preserved craters in the solar system. Why? No water, no erosion. There are other things besides impact craters on the surface of Venus. These, rather than being pits, should come out at you. These are two actually small volcanoes for Venus. Notice the scale. On Earth, these would not be small volcanoes at all. There's an impact crater up there. Venus also has 500 features called corona. Corona means crown. These are tectonomagmatic features. Kabuchi corona here is a pretty typical corona. They range, the median size of the corona are about 200 kilometers in diameter. This one has radial fractures going out. You probably or hopefully also see radial flows coming out here and some concentric structures around there. To date, Venus is the only planet that we have recognized corona on. And these, as I say, there's 500 of them on the planet. They're mostly in chains. A few of them are in clusters and very few isolated. We're not going to talk about them very much, but I do want to take you through just to say that you've gone to Venus. Here's another corona, Hatahensik corona. This should be a very deep trough that you should see topographically there, and a high. Another corona up here, Miralaji, another corona over there. You can see that circular feature is used relatively freely. Of note is that Hatahensik, these troughs right there and the troughs over here and here and here were proposed early on to be subduction on this planet. We can pretty much show that that's not the case. In fact, the simple curvature is much too much for the dynamics of subduction, and then we can trace features from what would be the upper and lower plate, as well as flows from what would be the upper and lower plate, and so these are not features of subduction. Whoops. Venus does things very large. This one might be hard to see because of the size. Note the scale up here. This is a huge volcanic complex. There's a smaller volcano there, but volcanic complex there, which is part of this overall complex. This is what we call a volcanic rise. And these are young features. They're contemporary features. They are held up by basically big mantle plumes. Think of Hawaii without the plate moving, just staying in one place. We're going to look very briefly at other features. Well, volcanic rises, remember, are contemporary features. And we know that from their gravity topography ratios to show that they are held up thermally. Other features that are a similar size to volcanic rises are crustal plateaus. This is the topic of the talk today, are crustal plateaus. Notice the scale again. Hard to see, actually, the topography of this because they're steep-sided and flat-topped, hence the name plateau. Very radar bright across the whole surface. They have a very distinctive and unique fabric that marks all of the crustal plateaus called a Ribbon-tessera terrain. And we'll be looking at that later to understand something of how they form. Okay, glasses off for a little bit, or you can leave them on, but you'll probably get sick. When we look at Venus's topography across the planet, unlike the Earth, it's unimodal. And so here we have on a plot percent of the surface and elevation, but we use mean planetary radius as our reference point because there's no water, so there's no sea level. And we can see that there's a big peak here. The regions that are high, we creatively call highlands. The regions that are low, we call lowlands, and in between, the mesolands. And you can see their distribution here. And I've got, remember I talked about volcanic rises, contemporary features, and crustal plateaus, ancient features. These are the largest single geomorphic or geologic features on the planet. We're going to talk about crustal plateaus today, and those are shown here in the blue. Volcanic rises, though, I also highlight shown in red. And you can see that each of them are scattered somewhat across the planet. Two other unique features we won't be talking about today, but if you come to the public talk, we'll talk about is Artemis here and Ishtar-Terra there. When we look at these now back on a globe to understand a little bit more of the Venusian geology, we have Atla Regio, which is a volcanic rise, so a contemporary huge plume feature. You can see sort of arms going off like this, and you can probably envision that those are rift-like arms, and that's probably what they are, but the planet doesn't actually rift apart because there's no place for the planet to be able to, or mechanism to be able to recycle that. We have Thetis Regio. Here is a crustal plateau. The lowland regions are called Planitia, and here they are in blue. Another view, we're looking down the North Polar region. The Planitia, I didn't give the names, it doesn't really matter, are in blue here. Beta Regio, another volcanic rise. Ishtar-Terra, you can just see that it's made up of, the whole thing sits high, but it's made up of a lot of different types of terrain. Similar to the way Pluto's made up of a lot of different types of terrains that we didn't necessarily expect. An equatorial view here, we have three crustal plateaus kind of all lined up. Artemis there, another plateau, Tellus Regio. This is one we looked at in 3D all by itself. There's another one elsewhere by itself. The way that we tell the crustal plateaus from the volcanic rises here, Bell and Isla, volcanic rises will have a broad domical form, which is consistent with their thermal support. Crustal plateaus are steep-sided and flat-topped, and they are supported isostatically by low-density material underneath them. So we're going to talk about crustal plateaus. Here are the features of that. So crustal plateaus. This is a stereo image, but I don't know how much you'll actually see. If we were to zoom in, there's actually a fair bit of topography, but at this scale, you might see that there are some lows and highs within this. What's important is the definition of these, or characterization. They're quasi-circular, they are plateaus. Size, they're big. They all have a very unique surface fabric that we call Ribbon-tessera terrain. They are supported by low-density material, either in the crust or the upper mantle. I think it's in the upper mantle. And everyone agrees that they're ancient features and that they formed on thin lithosphere. Here is that Ribbon-tessera terrain. It's not stereo yet, but we'll get to that. Folds of this orientation and perpendicular extensional structures. And we can map out all of those features, and here we see the distribution of the Ribbon-tessera terrain. And there you can see that they kind of make a circular feature or line up in belts. The big blobs would be Crustal Plateaus. When we spread those out and look at the Ribbon-tessera, it's in the Crustal Plateaus that we see here, but we can see that it's also in lowland regions, mean planetary radius, altimetry over there, like this feature that we see over there. What's important about the Ribbon-tessera terrain is that it is exposed across 12% of the surface, and these are true exposures. It's not like the exposure that we have on Earth because there's no burial. That's the bared, buck-naked Ribbon-tessera terrain is 12% of the surface. But we can also see that 20 to 35% of the surface at a minimum is shallowly buried. We can make those inferences by putting pieces together there. When we look at them in the lowland regions, they have folds, and they have, which are contractional structures, and perpendicular to those are extensional structures. And we can map those out. Now the Ribbon-tessera is in the light blue here, but the folds, axes go, crests would trace around equivalent to this topography, and the ribbons are perpendicular to that. So we can start to map these out, similar to the way we would map out Archean gneissic terrains and map them, see how things would relate to one another. By doing that, we can start to say, this is one entity here. We can map out other entities here, and we can start to begin to see cross-cutting relationships across the planet. Another story, but we can see these things. This is really important because when we start to see these large global patterns, what that says, and these are the oldest terrains on the planet, everyone would agree that if we had plate tectonics, these would be disrupted, and they clearly are not. So when we go to the Ribbon-tessera, let's look at, if we zoom into one of these crustal plateaus, Thetis regio. There's Thetis, the brown is the exposure of the Ribbon-tessera, and I've just put at the same scale here the superior province. If we look at Thetis, Thetis has broad warps that we can map within the surface, and here are the warps, and those are similar to the aniformal warps that are across at the large scale of the superior province. I jokingly say, notice they're even the same orientation, so they must have formed in the same way. I don't really mean that. If we zoom in on the Abitibi that we saw before, remember we looked at the crests of broad regional warps at the scale of the Abitibi here, and we can similarly go to Crustal Plateau Avda Regio, and this is Ribbon-tessera that we'll take apart, but broadly we have crests of large warps here, troughs in between, a crest, a trough, and those are at a very similar scale to what we see in the Abitibi. We're going to zoom, oh no, before we do that, another thing that happens to the Ribbon-tessera terrain is we see these incredible late ductile shear zones. This is in a large tract of unnamed tessera. There's your scale, and you can see these beautiful ductile shear zones. There, I've just highlighted them in purple there. And curiously, we see late ductile shear zones also within many of the Archean terrains, including the Pilbara shown here. If we zoom in now at what this Ribbon-tessera fabric looks like, because it turns out to be very important in terms of how these features form. So yeah, you guys already figured out this is a synthetic stereo image, and what you should be seeing are folds, generally in the orientation of the, that I'm moving the pointer right now. Lots of different wavelengths, and perpendicular to that you see sharper features, some graben complexes there, and then more periodic structures here that are ribbons. We also see regions that are radar smooth. These are flooded by lava, and you can start to see timing relations where this graben complex right here is cutting across that fill, but this fill of lava is in the trough of a larger scale fold. We can zoom in to this. At all of the Magellan data is digital data. It's just incredible that we're able to look at things in this way because the mission was put together in the 70s. in the 70s, and we had none of the computer technology that we have. We zoom in here, and again, folds of this orientation and ribbon structures perpendicular to that. There's that late lava fill, but we can work out the formation of when those graben complexes. What we see is that contractional structures are at this orientation, and extensional structures, the graben complexes and the ribbon structures, which are extensional, are perpendicular to them. Notice orthogonal. We see that extremely consistently across the Ribbon-tessera terrain. So what we do, back to this area here, we map these out geologically, so I've just overlain the geologic map on the synthetic stereo image. If you leave your glasses on, you can probably see the two of those, and one step further, now pretty much taking the image away, we make these geologic maps, and we work out what the geologic history is of the area. It's just basic first-order geology. What are the structures? What is the history? What does that then tell us about how things form? So we did that across large regions. Oh, before we do that, a little bit more about these ribbon structures. They are really curious structures. We don't see anything like this on Earth, and we haven't seen anything like this on any other planet. What the ribbons are basically north-south in this view. And what they are is very periodic, you can probably see, and they're alternating ridges and troughs, kind of like my fingers here, but with a very, very long aspect ratio. Steep sides, flat tops, extremely periodic and regular. You might notice tiny little wiggles here in the ribbons, and those wiggles actually are not true wiggles in the ribbons, they're the radar artifacts. And what you might be able to see in those is that this is a fold right along there. Some will see that in 3D. Then we'd have a trough of a fold, another fold coming through here. And these wiggles, as they line up, actually indicate to us, even without the stereo imagery, that those are folds because of the way the radar artifacts work. We can take those even further and see these are ribbons at this orientation, folds at this orientation, and now you can start to see wiggles right down to the resolution. And all of those wiggles are folds at this orientation, very small, short wavelength folds, and ribbons at a perpendicular to those. What's really incredible is how fine these get. These are actually true stereo image. Notice the scale here. These structures right in there are ribbons. They look like a corduroy fabric, and these are folds. Now they aren't orthogonal, but we've got just like a corduroy fabric folded. Even more folded up here, also a true stereo image. This sort of terrain and the last one occur over an area the size of the state of Victoria, of Australia. The very, very fine, close spacing of the folds and the very, very close spacing of the ribbons allow us to say something about the layer thickness that's being deformed across this region. You start to say, how do you do this? If many of you have seen, or any of you seen, the surface of a Pohoihoi lava flow, that might be what this looks like at yet a different scale, but that's exactly what it looks like is Pohoihoi lava. And in fact, that's probably a pretty good analog for how it formed. But note the scale. So we've got these two perpendicular trends of folds and ribbons, contractional structure and extensional structure, and I think we're done with 3D for a while. We can start to work out characterize those and really understand how this surface formed. I try to capture it here. We've got long wavelength folds carrying intermediate wavelength folds, carrying short wavelength folds, and then perpendicular to that are extensional structures. We can look at the layer thickness, as I said, as a relation to the periodicity. And what I want you to see is we've got extensional ribbons in the black and the short wavelength folds in the white. Notice that we have very thin layers, way less than a kilometer across these regions. And those are basically deforming the same type of layer. We can work out they're forming broadly at the same time. We can also work out the strain that's going on these. And with the thin layers, they have they're thin layers with the short wavelength structures, and they have very high strains, whereas the long wavelength fold structures have extremely low strain. Then you have to think about how is it that we can put this all together. And I won't go through all of the ways we can't. About the only way we can is we've got an extremely thin layer early on. We start to fold that layer, and then that layer, as it's thickened, is folded on longer intermediate wavelength folds, carrying this earlier formed surface piggyback, and then those are carried piggyback on yet longer wavelength folds. And during this entire time, what is happening is lava is leaking into shallow troughs all through the structure, all through the history of this development. And so what that leads us to do is what we need to form this fabric is a huge lava pond. It is the crystallized scum of a huge lava pond that we're just progressively crystallizing at, forming those earlier structures and leaking lava up to the surface. Sorry for going through this so quickly as to not convince you, but I want to get to some other things. This is something I did not expect that came out of the mapping at all. Did not expect. We have a huge pond of lava. The pond of lava is the size of an individual crustal plateau, okay, on the order of 2,000 kilometers across. How do you do that? I tried to do it by a plume. Trust me, I tried to do it by a plume because I had published lots of papers on these things forming by plumes. You can't do it by a plume. Hansen was extremely wrong. How can you do it? You could do it. This amount of lava that we need is similar to that of the large igneous province of the Antang Java Plateau, and that was proposed by Engel and Kaufman to be formed by a bolide impact. What is not important is whether this was actually formed by a bolide impact. We aren't going into what their reasons were, but that we can form that much material by a bolide impact. So we put a bolide impact through thin lithosphere, causing massive partial melting in the mantle. That partial melt goes upward and actually leaves the root that we see geophysically behind. Jones et al. Modeled this impact to see could we really get this in 2005, and more recent modeling has shown that absolutely there's no problem getting large amounts of melt. It's very high temperature melting, very high fraction melting. What do we need? We need a thin lithosphere and a large bolide. So let's take that back to Venus. We have a thin lithosphere because when crustal plateaus formed, they're the oldest, earliest formed things, and everyone agrees they formed on thin lithosphere. We put a large bolide through early on in Venus's evolution, but Earth's too. We had no shortage of bolides. Let's put the bolide through the mantle. What's going to happen? We have massive partial melting here. Interestingly, this bolide doesn't affect this whole region. It might fracture things, but it's going to make a damage zone around like this. In the mantle, it's going to cause massive partial melting. That melt rises up and is going to collect, and voila, we have our huge lava pond. Down below in the mantle, there's also an interesting story, though, because when you do massive partial melting of the mantle, what do you have? You have a mantle melt residuum. And that mantle melt residuum is very high magnesium. It is very dry, it's very strong, and it's buoyant. I didn't go looking for this, but that's what happens when you form the lava pond. What happens then? Well, that mantle melt residuum is going to rise up my pond, and so then, boom, I've got my crustal plateau. Now, that mantle melt residuum is in the ductile mantle. It could be swept away. If it is swept away, what's going to happen? My lava pond isn't high, and younger things can form deposits on it, and I see it in bits and pieces, just as I see on the lowlands in Venus today. But if that mantle melt residuum remains in place, and with secular cooling, I thicken the lithosphere, it becomes locked in place. I've got a crustal plateau. I flood around it, and there are my crustal plateaus preserved that I see on Venus. So I can accommodate both of those. So we can look at Venus, and we can say, OK, we go through these time steps like this, and we can form the lowland, or we can form the crustal plateaus. I'm going to speed up because I'm looking at the clock and going, okay, we have to get to the Archean. So we look at Venus, and these are Venuses. These are unique features on Venus. The Ribbon-tessera only forms in these old times, and they are formed on thin lithosphere, large bolides, so early on in its history. Well, we can look at the Venusian crustal plateaus and Earth's Archean cratons, and as I've shown, there are actually a lot of similarities. Similarities in style, similarities in magmatism and deformation forming at the same time, similarities in terms of being able to be preserved over the planet's history. So I'm going to postulate that the Venus crustal plateaus are an analog for the Archean cratons. What did we need for the crustal plateaus? We needed thin lithosphere and large bolides. Well, let's take those to early Earth. If we go to early Earth, we had a thin lithosphere. We had a hotter planet, and we can think about the lithosphere. I'm not talking crust here, just the lithosphere. The base of the lithosphere is basically an isotherm. So if we have a hotter planet, that lithosphere is going to be thinner. It's debated as to how thick it is, and those debates range from 20 kilometers thick to 70 kilometers thick. Their mechanism dependent on heat transfer, none of which we know for sure, but we are going to expect that we had a planet with thin lithosphere. Well, what was happening in the neighborhood at the time? If we look to the moon, there's lots of evidence of early large bolides. If we look to all of the other planets, Mercury, actually not Venus. Venus doesn't have that many craters. It has enough big ones, but that's another story in and of itself. But Mercury and the moon is the really great one to look at because the moon was hit by these things, not because it was running around and protecting the Earth, but because those bolides were headed toward the Earth, and the moon happened to be in the way. We actually now are getting evidence that we actually had large bolides even on the Earth during the Archean. There were 2 papers that were published in Nature in 2012. And one of those dealt with actually evidence of Archean spherules that we see. And these are the ejecta from large bolides, and Johnson and Malash used the spherules to actually be able to model the bolides and came up with a range of bits. This particular bed yielded a bolide of 41 to 70 kilometers diameter. Other modeling that is done is not on Earth, but done out in our solar system as to what caused the late heavy bombardment on the moon and how long it lasted. And the new modeling would say that if we look at the lunar or moon late heavy bombardment, this is the impacts in time, but on Earth we would follow a curve like this. I'm going to overlay on that. As geologists, when is the Archean? When are those Archean cratons forming? And they're forming in this zone of pink here. So we had large bolides, we had thin lithosphere. So when we look at early Earth, I think we really need to ask the question, what happened? What would happen if we have large bolides and thin lithosphere? Because I think we did have those. That's starting with what we had rather than a uniformitarianism approach of starting with today and moving back. Take that large bolide, Earth is going to be very similar to Venus. We're going to cause massive partial melting. That partial melt is going to go upward, and it's going to make a huge igneous province. I thought, you know, large igneous province is already taken with lips, so maybe we were making a hip. But a huge igneous province, the event of the impact is instantaneous, but the effect of this is going to go on for hundreds of millions of years, and that's really important to realize. In the mantle, we're going to have that mantle melt residuum that forms. We can go on up here to have this ultimately form our granite-greenstone terrain and gneissic terrains. There's the mantle root beneath them. And in fact, we can even, the depths of this are fine for forming our Archean granite. So we can form these roots as we saw them. We can form what we see at the surface. They formed together at the same time. And they're forming by a mechanism that requires large bolides and thin lithosphere, both of which had to have been going on. So if we look at the Archean now, we have a similar set of diagrams. Here we go through and we can form these. But if that, the residuum is moved away, then we have our granite-greenstone terrain now without its life preserver of support. And this material could and would be subducted on Earth once we started plate tectonics. If the life preserver of the mantle melt residuum remained in place, we have our preserved Archean craton. Now, once we form these cratons and preserve them here, they can still be butchered up and moved around as they are on our planet, but we also could have formed things like this and been subducted, as we did on Venus. So when we look at these two planets, I want to say that the Archean features that we see are unique on Earth. But I don't think they're unique in the solar system. And perhaps we can use Venus as an analog to at least expand our minds in terms of considering other hypotheses for the formation of cratons. To date, anywhere you go in the literature, Archean cratons are formed by endogenic processes. And to date, very, very few people talk about the role or any role of impactors in the early Earth. And yet we know that impactors, it was bolides that formed the Earth, and they almost certainly played a role once that Earth had formed. So we can look at these two planets and say that their baby book in their early years was actually probably quite similar. We may or may not have had plumes, thin lithosphere, bolides forming. We formed crustal plateaus on Venus that are still preserved. We formed Archean cratons. Some of the crustal plateaus were lowered and partially buried. Some of the Archean cratons became their roots stripped away, and they were recycled to the mantle, and we no longer have a history. Once we have plate tectonics, this process occurred only in the Archean. When we get to the point that the lithosphere thickens up, or we lose our large bolides, we are no longer going to form those unique features. They went their separate ways. Venus is very different, stagnant lid tectonics. Earth is into a plate tectonic mode. And by looking at the two of them in compare and contrast, we can learn more about planetary dynamics. So with that, I will end and take any questions. Thanks very much for your attention.